It's really a pleasure to be here with you. I'd like to thank the organizers, not only for giving me the opportunity to be there today, but also for organizing this amazing event with a vibrant group of people every time. It's been many years, and the group is still very vibrant and original in its ideas. So it's really great that it continues to exist. So 20 years ago, actually, I was starting my research career in this area of Paris. I was working at the Sony Computer Science Lab with Luc Steels. And at this time, I was very much interested by understanding the processes of cultural evolution, how new inventions were continuously being made by populations of agents, how they would be transmitted. And one of the particularly important inventions was language. And I can say that probably that cultural evolution processes are one particular kind of open-ended process. And we were building computational models, trying, for example, to understand how groups of agents could collectively self-organize a system of linguistic conventions, including inventing new conventions ranging from sounds to lexicon to semantic categories and to grammatical rules. And so there was innovation also in the creation of language and how to share it, how it would evolve with time, etc., etc. And we had really very successful results. We were able to reproduce a number of well-known phenomena in the evolution of world languages. So, for example, in my own side, I was focused more on the evolution of sound systems, and some of the models I was working with a number of colleagues could account for the duality between the diversity of sound system in the world and also regularities, like why certain vowels and consonants are more frequent than the others. That was all very, very stimulating. But one thing that all those computational models was assuming is that those agents would systematically be motivated to always want to play with each other, to communicate with each other, to share meaning and achieve joint tasks. And so this ingredient was absolutely essential for the system to work. And since we were interested into the origins of language, it led us very naturally to go to the question, where does this motivation to systematically want to communicate with each other come from? And so one possibility, of course, and actually defended by a number of people, was that maybe for some reasons we don't really understand, at some point there was a specific motivation for linguistic communication that appeared in ancestors of humans, making that, for example, babies and humans all their life, they want to communicate with each other. But we digged up a little bit more, and actually, if you begin to think like this, and you look at the development of the child, it may become problematic. The child is indeed at his individual level also kind of an autonomous and open-ended learner, in the sense that all the life, it's continuously learning novel skills of increasing complexity along a self-organized curriculum of learning. And it ranges across many domains. There is not only language, there is all the different areas of mastery of the body, ranging from locomotion to grasping objects, but also manipulating all kinds of tools, including musical instruments, computer bikes, etc. And for all of those stuff, every time a child learns a new thing, something that's absolutely essential is practice, is systematic practice. And so then the question is, I mean, how do you explain how they come to systematically practice how to crawl, for example, how they come to systematically practice how to grasp objects. And then, of course, you could say maybe there is a specific motivation to grasp object, maybe there is a specific one to crawl, etc., etc. But it begins to be very clumsy in the end to have this whole set of very particular motivational systems leading them to being interested in particular stuff, especially because in the end, because of cultural evolution, there are new activities that are around in the environment. For example, if you cannot imagine easily an activity where you want the child to be systematically interested in doing bicycles or playing computers. So you might say also maybe there is imitation, which probably plays a very big role. And you might say like it's the social environment encouraging the child to do stuff. But it's really not always the case. There are many stuff that children do, want to do, try to do, and actually that the social environment tries to prevent. Every parent who has a child in the house knows that they are permanently trying to do stuff that are dangerous, putting the figure in the plugs, etc. And you're not showing any kind of thing like this, so they are not imitating you. You are preventing them, and they are still doing it. So there needs to be something else. And this is actually what led us to develop across the year a research program that was like really focused on trying to understand the core mechanisms that lead children to have this open-ended lifelong development. And this was part initially of building a field together with many of you that we call developmental robotics. And more recently, like joining some of the ideas we developed across the years with more modern machine learning techniques, we like to call that field developmental AI. And that field basically, at least from the perspective of our team at Flowers, we organize our research in three directions that are all centered on like trying to really understand the mechanism that enable humans and machines to develop continually new skill without like an engineer opening the brain, retuning things for every new task. So really in an autonomous manner. And we are basically investigating two families of mechanisms. There are on the one hand internal mechanisms which are motivational, and in particular intrinsic motivation, which I will discuss, which in everyday language we might call curiosity. And then there is another set of mechanisms which is related to language. And actually we are viewing language not only under the perspective of language as a communication tool, but also, and maybe even more prominently, language as a cognitive tool, as a tool that enables, for example, I hope I can discuss that in the talk at the end, to be creative in imagining for oneself new goals, new tasks that could be learned. And so this perspective of studying curiosity and language as engines of open-ended development, we've been trying to develop it first within a perspective where we try to build models to help us understand better humans. Then another perspective where we try to transpose some of those mechanisms in machines to make them more autonomous, more flexible. And then we've been working on several kinds of applications in the real world, and especially two families, which I will discuss today. One is assisted scientific discovery, like how can we build curiosity-driven systems that help scientists make new discoveries. And the second application domain is education. How can we build systems that actually stimulate curiosity and open-ended development in children? So I try to talk today about all those things, and because there is a lot, I will go actually very quickly on each of the things. It's just to start discussions. I will be there the 3 days. So if you have more questions, we can start. We can go on that after. So first, let's start by curiosity. Actually, that's a concept that began to be investigated and explored already in the 40s and 50s in the last century by psychologists like Berline or White and many others. And they were not satisfied by theories trying to explain the behavior, the learning, the exploration of children only based on what they later on called, Berline in particular, called extrinsic drives, such as finding food, finding social recognition, maintaining body integrity, etc. Basic physiological needs. And so they basically observe that probably the brain has some of the kinds of neural circuits encouraging it to spontaneously explore activities, for example, for the sake of surprise, for the sake of novelty, or cognitive dissonance. Or more recently, for example, we had people like Csikszentmihalyi saying that the brain likes to be in a situation where challenges or tasks are of intermediate complexity, not very between boredom and anxiety, like the theory of flow. And by the way, the Flowers team, the Flowers lab, in which this project is happening, is the name comes from flow. It's flowing epigenetic robots and systems at the origins. But actually, those ideas have been existing for a long time, and for many years I've been working on top of those ideas. But initially, I came to explore and study some of these ideas in a very different route. And many people, actually, including in the room, also came to explore these ideas probably in a very different route. On my own side, as well as also the colleagues with which I began to work on that early on, like Frédéric Kaplan, we happened to get into those topics through another field, which is theoretical biology, and especially the work of Varela and Maturana. And they had this autopoietic theory where they viewed cognition, and including human cognition, as kind of homeostatic system, which was continuously trying to maintain its boundary. And like when it was perturbed by the environment, it was trying to do something to go back into some kind of equilibrium state, including in cognitive state, like maintaining good predictions, for example. I was not convinced by this theory. I thought it was very convincing for many, many aspects, but I thought it was limited in terms of accounting for the proactive exploration that you see in organisms of all kinds, and humans in particular, which are not only reacting to perturbation to come back to an homeostatic state, but they search for perturbation. They go for perturbation. And so, at the same time, if you really go for perturbation too much, if you imagine some kind of explicit drive to go out of your zone of comfort, it might be pretty dangerous. And so that is the way we got the intuition that maybe what's actually rewarding and something that organisms are searching is not to be in the zone of comfort, it's to go back to the zone of comfort. And this is what progressively led us to a quick idea I will present in a few slides, which is the idea of learning progress, which is the idea that maybe humans and the brain and the brain of other animals, they like to be in a situation when they learn about the environment where they are coming back to better predict. They don't want to predict well, they want to go back to better predict. And that's pretty different. But then actually later on, there are a few people, especially Andy Barto, who took the effort 15 years ago to go into libraries, and he discovered all this literature and psychology. And one day he came to see me and he said, well, all the things that, because he was also working on that, all the things we are trying to discuss, they are very connected to all the work of Berlin and One, etc. And this is the way we began to link all this up. And indeed, I mean, similar ideas were actually began to be explored by different communities. Okay, yes, so sorry, so something I forgot to say is that something that was very also fundamental in what we were trying to do at this point is that our main objective was not so much initially to build really smart machines. We were using machines as tools to model humans and to understand better humans and the way children develop. And I believe it's probably also the way people like Gianluca came into these topics. Maybe not, he can confirm or infirm. But there are other people like John Andrea, Spielhuber, or Andy Barto, who came to this topic from a different perspective. They wanted to build more flexible machines from the start, and they didn't really care how to model humans. And then there is another community in the evolutionary computation who also developed very similar ideas at some levels, but again with different origins. Okay, but just to now take a step back, something that's been very, very common in many of those views, especially when we are trying to model child active exploration, is that we've been saying a child as little active scientist. So he's basically like in an environment and he's trying to build a model of the world. And to build a model of the world, he's trying to make experiments. And then when he makes experiments, he makes various kinds of predictions. And then he does the experiment, he observes the results, he adapts the model. So very classical learning. But then the thing we've been working on is the loop on top of that is some kind of metacognitive loop, which basically is the engine of selecting what kind of experiments to do in what kind of order, in what kind of curriculum. And that's based typically in most models on building some form of meta model, how much uncertainty, improvements, empowerments, certain situations are providing and leading to the internal generation of experiments. And actually, there are two major families of experiments that have been considered. There is one family of experiments which we could call prediction experiments. Like, for example, imagine the children are in a situation, they say, okay, let's mix this and this chemical. What could be the result? They make a prediction. That's what we've also called knowledge-based intrinsic motivation systems. And then there is another family of experiments, which I believe is very paramount in human development, is instead of like making a prediction about what's going to happen, for example, these children, they say, oh, maybe we could imagine building a tower like 2 meters high. Like, so they imagine in their head a goal that they'd like to achieve with a certain budget of time, and they go for it. And after a certain amount of time, maybe they assess how well they did, and they give feedback to themselves. And so I'm not going to describe the whole history of those two families of stuff. I just want to take a shortcut, and I go directly to this kind of systems, which I believe is extremely powerful. And so this kind of system has led to what we've been calling Autotelic agent, which is basically a shorthand for intrinsically motivated goal exploration processes, which is a family of algorithms implementing the following process, which is like a continual loop where basically an agent is first sampling a goal, given a space for representing goals. And then after sampling a goal for itself, is going to allocate a budget of time to try to, I'm breaking everything, to try to pursue that goal, given its current model of the world, its current goal condition policy, for example. And then it's going to assess again for itself internally how well it's doing for that goal, which means actually that the representation of goals, when it is sampled internally, comes with a way to evaluate it. And so it means that in general, the way we are considering the concept of a goal is that in general, mathematically, it's a vector parameterizing any aspect of a problem in general, as well as a function associated to it, which enables to assess how much the goal has been achieved. And then after that, after the feedback from the environment, various kinds of internal models can be updated. And so there is many labs in the world.
If you unplug the switch,
which one?
I think you unplug the network switch.
Ah, it's the switch. Okay. Smart. Okay, so I should not move.
That should come back.
Okay, so now I can explain one particular aspect of the power of such Autotelic agent, which is hindsight learning. So initially, I didn't actually aim to unswitch the switch, but now that I've done it, I can say, okay, if my goal would have been to like unswitch the switch, which plug should I put out of it? And now I know.
You're probably disconnected from Zoom.
Yes,
yeah,
we're disconnected.
And
share again.
There, I have to share. I have to connect again, actually. Okay.
Yeah.
Are we good? Yes. Okay, thanks for that. Sorry for the little animation. So many people in the world, many labs in the world have been working in the last few years in different aspects of these loops, including in the not only in the IMOL and the ICDL communities, but also in the more classical machine learning communities, where this kind of system are becoming relatively standard. And there are many open challenges here, like how to represent goals, how to learn representations of goals, how to sample goals, what kind of learning architecture should be used to learn how to achieve goals, how to update the models, what time scale does it happen, etc. So first, a few quick comments about, imagine you know how to represent goals, you have a representation of the goal space, how you sample a goal. So just quickly, like for those who know, so that they can see where this fits in the picture, one of the ideas that we've been working on across the years is the idea that one particularly powerful mechanism to select goals in an environment where there are many possible things to learn, too many to be learned in the lifetime of an agent, many of them very easy and trivial, it's not very useful to spend time on it, many of them unlearnable, too difficult because you cannot observe latent variables, etc. So it's useless to spend time on it. And so the question is, how do you organize yourself to use your time efficiently to learn a diversity of learnable goals within the amount of time of the life? And one mechanism that's been very useful and shown in many experiments is the idea of learning progress. Imagine you have several kinds of goals with different potential learning curves, which you don't know in advance, but they are like this, where the idea is that initially you begin to sample them more or less equally. You make an internal models of the rate at which you're progressing across the different kinds of goals, and then you're focusing more on the one in which you make more progress. And then at some point you reach a plateau, you switch to the other one who is providing learning progress, another niche of learning progress, while avoiding goals that are either too easy or too difficult. And so this is just self-organizing the learning curriculum. And this idea, we've been for a number of years trying to use it to explain, account a number of developmental phenomena we observe in infants. For example, various major stages in vocal development, various stages in the development of tool use, but it was still theoretical. And very recently, in the last 3 years, I would say there are a few labs in the world, some people in my team, but also 2 groups doing completely independent research in other groups in the world that actually develop new experimental paradigms to test the learning progress hypothesis, and where basically they develop paradigms where they present to human subjects various learning tasks where that people can actually choose freely in a given budget of time. And one try to study the structure of the way they explore the learning tasks. And then we are considering various models of their utility functions, and we are trying to assess which utility function is explaining best their behavior. And those 3 recent papers actually confirm that learning progress is an important component of for the decision of in spontaneously exploring various learning paths. Okay, but then actually learning progress, I would say, in the whole story I want to tell today is only a secondary concept. What's more important is the concept of goal exploration, and actually goal exploration, even if you sample relatively randomly goals that are beyond what you know, with various kinds of mechanisms like hindsight replay, which I demonstrated physically a few seconds ago, you can learn a lot. You can learn surprisingly efficiently. One particular experiment where we showed that was this a few years ago, when we had this kind of humanoid robots. And here, the engineer would provide tools to the robot to perceive the environment, like the position and speed of objects, their color, their sound. And also, the engineer here provided by the hand a system to represent the goal. And here, it was really like a system for coding the trajectory of objects in the environment. So that was pretty high dimensional. I think it was a few dozen dimensions for each object. And so as a whole, the goal space for all objects was like 300 dimensional. And in a matter of 20 hours, those robots, they were managing to learn how to use various tools and objects in this environment. So that was really very powerful. And the same kind of idea also was used in other domains by people trying to solve difficult video games that were used as benchmark in the early days of deep reinforcement learning, and some of them were unsolvable. And actually, some algorithms that can be formalized with intrinsically motivated goal exploration processes, like in the quality diversity algorithms, show that actually it can be key to actually solve those engineering problems. So this is the kind of work that made the first step, showing that it's not only interesting for modeling humans, it's also very useful to solve hard engineering problems. But then one limit of those early works is that, for example, both here and here, the goal space is basically hand-defined, concrete, fixed beforehand. So one question that people began to ask is how can artificial agents also learn how to represent goals they could sample by exploring the environment? And so what various groups began to do is to use unsupervised learning methods, for example, variational autoencoders. And so like typically the way it happens is that initially you have a robot trying a few random things in the environment, collecting images, training a VAE to learn a compact representation of those images, and then learning the latent space as a space in which to sample goals representing regularities of the space. And typically what people have been doing is that initially the discoveries are relatively stupid and simple, and so the VAE learns very, very simple things. But as goal exploration proceeds, there is new data, more diverse that arrives, and the VAE actually evolves its own representation of the environment. And so the representation of goals is actually evolving as well as the discovery. However, a limit of this kind of approach is that the goal representation has, in that setup, is always basically the same kind of low-level concrete goals. It's always a representation of this VL. Even if it evolves at a given moment in time, he has a single representation for all goals. And it's very concrete. So now let's see how we could address those limits and why they are important. Maybe having several representation of goals and having higher level representation of goals. And maybe for the first topic, I'd like to illustrate it in the context of an application of this work, which I believe is motivating well what I'm going to explain. And that's the idea that we could potentially use autotelic exploration algorithms to help scientists explore complex systems. Maybe actually to help them explore open-ended systems. So in the world, for example, chemists explore, when they study the origins of life, complex chemicals, which might have a very complex dynamics. Biologists explore morphogenetic systems that we want to understand. Cosmologists explore the formation of galaxies, etc., etc. They have computational models. Something that's common in many of those systems is that many times at the when they start studying the system and often actually even after many years, scientists don't even know how to represent well the diversity of potential structure that can self-organize. They don't even know what's the map of the possible structure that are possible in a given self-organizing systems. And many times, like they are in biology lab, physics lab, the way they explore is really by the hand or by like research. And because many of the systems are very high dimensional, it's actually like very inefficient. So basically they have difficulties making discoveries. And so actually you can actually use the autotelic exploration algorithm to do that better. I think one of the first examples doing this was Jonathan Grezou, who was a PhD student in the team some time ago and joined a chemistry lab in Glasgow from Leek Running. And they are studying the origins of life and they are studying oil droplets. So here, this is various oil droplets with different kinds of oil, different concentration, and they are really self-organized in multiple very rich ways. And if you look it by your human eye, it's very easy to imagine anthropomorphic terms to describe their behavior. They believe it's a very important step potentially for the origins of life. But a few years ago, they were still at a stage where they were really like by the hand trying different stuff, very, very inefficient. And they didn't know how to represent those stuff. So the first step was actually to roboticize the lab. So Jonathan participated to build those robots to mix automatically the stuff. But most importantly, he equipped those robots with autotelic exploration algorithm, actually the same one as with the blue humanoid robot you saw before. And in the first series of experiments they made, actually they could show in the paper I just showed before that by doing that, they could actually discover, even with a very simple handmade representation system of the goals, a much wider diversity of behavior than they knew before. But still, one limit of what they did is that they like by the hand define a goal space, like one dimension is the average speed of droplets or the average number of droplets. Very simple. How can we do better? So we try to improve that in the lab, but because in the lab we don't do chemistry and we don't have like this kind of robots, we chose to work with another family of systems, which actually biologists have been using for long to model fundamental processes of embryogenesis, which are cellular automata. And so you all know the game of life, in which it's possible to self-organize gliders, which are kind of little creatures. But something that's very interesting in recent years is that people have developed more complex versions of the cellular automata, continuous cellular automata. And in both cases, one open scientific question is to find like localized patterns that behave and move around, like maybe self-organized agents. In the game of life, actually, it's very common to find gliders, but it's mostly impossible to find robust gliders, like gliders that can be robust to perturbation in the environment, that can have forms of self-maintenance. When those systems were invented, it was also an open question whether we can find this. And so we said, let's try to use our autotelic exploration algorithms to see if we can find such stuff. But the thing is that in those kind of systems, you can have really many different kinds of patterns self-organizing. Like, for example, patterns filling all the field, stripes, sometimes little things moving, and they are qualitatively very different. And so intuitively, you say, maybe I don't want to represent all these kinds of phenomena the same way. Maybe I need several kinds of representations, but I don't know in advance. And so this is what led us to the idea of meta-diversity search, and especially that's an idea developed in the context of the PhD of Mayelen Echeverry in the team. And this is the idea that instead of having an autotelic system incrementally learning representations of its new discoveries within one latent space, it's going to incrementally create new spaces when there are new kinds of behaviors appearing. And then it's going to lead to a diversity of goal spaces in which the autotelic agent is going to search for a diversity of goals. So it means that now actually the autotelic exploration loop has two steps. First, you choose which goal space you want to aim for, the representation, and then you choose what goal you want to reach in. And the way actually we worked about that, and especially Mayelen, who did all the experimental work, is that initially the system is learning basically one coarse VAE to learn a latent space, but very quickly it's discovering that in this coarse VAE, there are different kinds of phenomena, and so it's creating a sub-representation with two new branches, like a tree of VAE, to specialize in learning various kinds of phenomena, and it's going to do that hierarchically. So basically, in the end, it's going to learn a hierarchy of diverse representational spaces. And what's interesting is that the system is going to explore a diversity of different kinds of patterns in these different spaces. And it's also possible to include the scientist in the loop. For example, if the scientist is interested in patterns that are filling the space like this, maybe the scientist can say this kind of goal space, like just by clicking and saying, like, this one I like, this one I don't like. The autotelic exploration system is going to specialize for this kind of discoveries. And here is another kind of discovery that's made more with localized creature, and this allowed us actually, we don't see it here. This allowed us to actually discover the first gliders in these environments. But at this point in time, they were not very robust, and so just for the curiosity, for those who are interested, we fine-tune those methods, and actually we focused on trying to find robust sensory motor agents in cellular automata, like gliders that basically can maintain their integrity, behave in a sensory motor way, like avoiding obstacles. And so these are the results you can see here. You can launch bullets into these creatures. They reconstruct themselves. You can erase half of the body. They reconstruct themselves. It's not something that's been optimized explicitly, so they are extremely generalizing to their environment. If you put them together, very interesting dynamics happens. They maintain their individuality. Like when they bump into each other, they move around. But sometimes there is some stuff happening, and they kind of reproduce. And just as a last step, because I'm very excited about this, we recently introduced a variant of the Lenia environment where we have mass conservation and also localization of the parameters of the rules. Basically, the physics is localized. Like the physical rules of those environments evolve like with normal degree of matter. And the consequence of this is that you can have the self-organization of creatures with really different local physical laws. And because they mix up with their neighbors, we believe it's really like what could be the origins of some form of emergence of evolution. So just for the curiosity, on the left here, you see the kind of stuff that's happening. And so you're going to see emergence of stuff looking like multicellular structures, like here on the left. And here, you're going to see maybe the emergence of eating and growing. Look at this orange stuff with the other creature. Okay. Stefan, how much time do we have?
5 minutes.
5 minutes, okay. Okay. Okay, so this part was about illustrating the idea that beyond learning a representation of goal space in which you want to search for diversity, it's very important also to be able to learn continuously new representations in which to sample goals, so new goal spaces. So I believe this is one important aspect of open-endedness. Another important aspect is to go up in the hierarchy of abstraction. In the metadiversity experiment I just showed, we really had a diversity of representation of goal spaces, but in a way, they are all structurally similar. They are like, from a bird's eye point of view, they are really like similar. They represent things differently, but they are like similar. They are concrete. They are not very abstract. Humans can also imagine very abstract goals, not only concrete ones. And so one of the tools they use a lot to imagine more abstract goals is language. And this is an idea that has been developed by various psychologists, including Vygotsky, who's defended the idea that language is fundamentally a tool to think beyond a tool for communication. It essentially learns to communicate with each other, but then language is conveying various ways to conceptualize the environment, various thinking heuristics, which are then internalized, and the agent or the human, when he's thinking, is speaking to itself and using language as a generative system to imagine new stuff. For example, new goals, like this little girl imagining maybe what could I draw today? Let's combine the word cat and the word bus, and maybe we can draw a cat bus. So apparently she was maybe not the first one to imagine that. So one first step in this direction, we made it a few years ago, and it was in particular the work of Cédric Collat and Tristan Karch. Cédric, you will hear later on. We explore the idea in a very simple environment, which actually has a dynamic that is a bit similar to Minecraft, where you have an agent, a little hand that can combine various kinds of object and materials to build up new ones. Of course, visually much more simple. We are not really experts in complex environment, but that's the same kind of idea. And then there is a social peer around. And initially, this little agent is moving around randomly, doing more or less random action, and sometimes by chance combining objects. And when this agent is doing something that's interesting from the point of view of this social peer, the social peer provides a linguistic descriptions of what the agent has just done. And with this association between its behavioral trajectory and the linguistic description, the agent actually can learn many things that could be learned later on. First of all, it can be an example of how to of policies achieving a particular linguistic description, but more generally, this mapping can be used in multiple ways. It can be used, for example, later on as a goal achievement function, because it's a measure of how well a sentence and a behavior are matching. It can be used as a captioner, if you have a behavioral trajectory, you can try to generate by optimization the sentence that is matching best. And it's also a way to learn a generative model of the language produced by the social peer, which you can also use in various ways. And actually, those uses are made in the second phase. And in this second phase, now the agent is not exposed anymore to feedback and description for the social peer. He is in the environment, and now he has the ability to use the learned language model to recombine the words in novel ways to imagine new goals. And because language is structured in a particular way, is conveying concepts that are salient to the human, doing that has a probability to generate goals that might be interesting and feasible that is much higher than generating random goals in a random embedding representation of the environment. So he's generating goals that way, and then he's going to use the learned goal achievement function for self-assessing how much he's doing at the goal. And he's also actually going to use the captioning abilities of those learned association to do hindsight learning, which is the demonstration I made to you a few minutes ago. And so through a number of experiments, we showed how this would allow really efficient exploration in combinatorial environments. So I'm not going to describe you the curves. There is a great paper by Cédric, but it's really like a powerful way to explore and to go beyond the examples and the guidance of the humans. But one limitation of those early work is that the language was very simple, and the environment also was very simple. And so recently we began to explore the idea of how can we scale up to more complicated language, more complicated environments. And this is work that was led by Cédric Collat and Laetitia Teodorescu. What they've been doing is consider the use of a large language model, in this particular case ChatGPT, as a proxy to human culture and language, which can be used as a cognitive tool by the agent directly, and exactly in the same way as I just described. as a way to generate goals, as a way to relabel what has been done after the goal has been tried to achieve, and maybe it has failed, but maybe it has done something, and as a way to assess the goal. And so here we've been playing with what's called text world, which are video games. Everything is in text. Here it's like in a cooking environment. So typically the game, you are in the kitchen, in front of you, there is a banana, there is an apple, and there is bread and whatever. What kind of thing do you want to do? I want to put fire to the kitchen or something like this. And the LLM is suggesting various kinds of goals based on what it has achieved and not achieved in the past, for example. And here the first results are really interesting in the sense that it enables with very, very little hand programming from the part of engineers to have this system actually make new discoveries and increase its repertoire of skills in this kind of environment. Now, and actually, probably recently you've heard, because it's been very popular, the Voyager system from NVIDIA, which is basically a Minecraft agent that's kind of autonomous on exploring the environment and learning how to build diamonds. And it's basically more or less exactly the same architecture. This was parallel work. The difference is that they have a little bit more resources, a little bit, so it's more beautiful, but it's basically the same. And so I like to show it because it's actually illustrating really the same idea. And so what they did here is that they actually used Minecraft as a text world. So they are not dealing at all with the images, that like they are using a library that says to the agents every time step, at this location, you have a tree. At this other location, you have an axe. Here you have some stone, whatever. The list of action is that you can that you can use is this one. Okay, now which next goal could you suggest? And it's really asking it to GPT-4. And then after the GPT-4 suggests the goal, they are also using GPT-4 to suggest a Python program to solving the task. And then it's actually trying to execute the program, trying to fix it by interacting with the environment and using the textual feedback from the environment. And when it's working, it's putting it into a library of skills, which can be reused for building higher level skills later on. So that's really a pretty nice Autotelic exploration system, one of the most impressive so far. And actually, this agent ends up mining diamond tools. And just as a conclusion, for those interested, we are beginning in the team to further this direction by considering maybe an even more open-ended environment than Minecraft, which is just the general space of Python programs. So we are considering now building Autotelic agents that are going to develop, hopefully open-endedly, their programming skills. And so here we have agents who invent their own Python programming challenges, and they try to learn to solve that. And so they are using a language model to invent those new problems given what they've been doing in the past, succeed, not succeed, etc. They use the language model to suggest Python ways to solve it, and they use the Python interpreter as the environment to get feedback. And so that's the work of Laetitia Teodorescu and Julien Pourcel. And so, oh yeah, so I won't talk about this educational, but we have a super cool educational project to train children to develop metacognition and curiosity, but I don't have time. As a conclusion, take-home message, open-endedness. It seems to me that something that's pretty important in open-endedness is that very often we observe open-ended system generates other open-ended systems. Biological evolution is open-ended, generating open-endedness at the level of individuals, which as a group generate open-endedness at the level of cultural processes. Open-ended systems are often characterized by the generation of novel kinds of novelties. So there is a form of meta properties in open-endedness, and actually we could probably decline this concept into nth order open-endedness, like zeroth order is like generate and achieve and learn new goals, but always of the same kind. First order new goals in new goal spaces that are continuously created. Second order new goals in new kinds of goal spaces. Third order new goals in new kinds of goal spaces, etc. And something that's a corollary of what I'm saying here is that because novelty is measured within the perspective of a particular representational space, the representational space being used by a particular observer or cognitive entity, whether it is the learning agent itself or a scientist observing the system from the external, it means that from that perspective, open-endedness is fundamentally a subjective property. And I believe it's completely okay, but it's important to understand that as a way to make progress to understand this properly. And so as a last word, I have to say that some part of the discussion I presented today is the result of recent, very interesting discussion I had with Olivier Sigaud, Clément Moulin-Frier, Maëlène Echeverry, Cédric Collat, and Laetitia Theodorescu. Thank you.